So, electromagnetic induction. I've put this PowerPoint, um, on Canvas. So this is stuff from last year. So magnetic flux. Okay. So this is you're looking at how much magnetic field goes through this area. Okay. Mathematically, they like doing it as a dot product. Personally, conceptually, like that's fine and dandy, but they make the area vector perpendicular or orthogonal to this area, which to me, yes, we can represent it mathematically, but for me, I like to think of it like how much of this magnetic field is passing through this. So I look at it from a perpendicular point of view. Like this would be, the magnetic field would be perpendicular to the surface. That would be greatest flux. This would be no flux because the area is parallel. That's how I think of it. Okay. So it's the area multiplied by the strength of the magnetic field. Okay. Flux is in Webers. Tesla meter squared. Good with that. Okay. For electromagnetic induction, we have two things. So this is a necessary measurement. Okay. For electromagnetic induction, we've got two things going on. We have Lenz's law, which was last year. I don't know if you remember, like, hey, it opposes the change in magnetic field. So we go this, and then that. Remember that whole thing? That's this. Okay. So there's an induced magnetic field that opposes the change, induced current that opposes the change in flux. And we'll walk through several examples of this. Okay, that's Lenz's law. It's conceptual. There's no math to that. It's just this idea. And then Faraday's law, which comes up with the value. So this will give us the direction. This will give us a value of stuff. So Faraday's law looks at the rate of change of magnetic flux through an area. That's equal to the induced EMF, the induced voltage. Okay. The negative sign is a direct application to Lenz's law. That's why that negative sign is there. Okay. And N, it would be the number of loops. The more number of loops you have, you just multiply that out. Okay. Now, the crazy thing is, for a change in flux, you could be changing the area. You could also be changing the magnetic field.
Or you could change the orientation. Well, that would be completely changing the area because area is.
Okay. So the way we deal with that is it's the product rule. Is that the name of that? Okay. So just the magnetic field times the derivative of the area plus the area times the derivative of the magnetic field. Okay. Yep, induced voltage. Okay, so this is how generators work. Okay, so you had this last year. This is new because we can now do calculus with stuff. Okay.
That's what I wanted to do.
Yep. Okay.
How's it rotating?
It's this way.
Okay, so it's rotating like this.
Coming. Yep. Correct answer is
yes.
Yes. Okay. we're changing the area of the window that the magnetic field can go through. Good with that? So like here, if you looked at it like light going through this, that window of opportunity is diminishing. Okay. So I'm going to walk you through this one first. So we're decreasing the field. Okay. So the direction of the magnetic field is into the board. Okay. So the direction of flux is into the board. I don't care about that. I care about what the magnetic flux is doing. It is decreasing. So the direction of the change in flux is going this way. Is this decreasing? The induced magnetic current creates a magnetic field that's in opposition to this change in flux. It's holiday stuff. Sorry, don't ask him. The change in flux is coming out of the page. The induced current creates a magnetic field that's in opposition to this change in flux. So we have a clockwise current. Yep. 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 Always opposes the change in flux.
So if the flux is going into the page, then it'll be going this way?
Correct. The change in flux was going into the page. It'd be that way. If it was increasing. Okay. So we're taking this and we're like whoop, squishing it.
Okay, so you're not rotating it.
Right.
Because otherwise I'm like, would it find those things? Well, other than the fact that I can't, other than the fact that I can't, other than the fact that I have a difficulty finding clockwise and counterclockwise.
Well, I think anybody would.
Correct answer is B, counterclockwise. So magnetic field's coming this way. We are decreasing the flux because the area is decreasing. So the change in flux is going this way into the board. And so the current induced creates a magnetic field in opposition to this change in flux, counterclockwise. Tell your neighbor.
Hey.
Good job. Coming out, increasing. I like it. A. Okay. Bless you. Bless you.
This is the thing that you drop the.
Yeah.
Yes.
I don't know what you're talking about. So.
Correct answer is
B.
C. There is no change in flux. Okay. Correct answer. Are you ever quiet? When you talk, you don't ever. I've never heard you whisper. I know. Everybody hears it. Here we go. Correct answer is A.
I probably don't hear it because I don't know that's me.
So the flux is decreasing. So it's going this way. The change. Good.
Oh, okay, the right part. Oh, jeez. I know.
I have an answer. Whether I was correct, I do not know.
I was gonna say.
Tell your neighbor.
And
I was thinking it. Because the field's increasing as it gets closer.
So field lines go out of north into south. Okay. So as you go through, the direction of the magnetic field is to the right. It's getting stronger. So the change in flux is to the right. It's the opposition to that magnetic field going this way. Hey. There's that. Correct answer. Tell your neighbor. There we go. We're having change the current. It's when the current is changing. It's when you have a changing magnetic field.
this is why
You have a
transformers work really well with
changing flux. Okay, good with that. Not when it's on. It is creating a magnetic field when it's on, but there's no change in flux. Okay. Okay. Okay.
Sorry.
So everybody go to D. Okay. Okay. Correct answer is C, based off of that number of loops.
Okay, I could have.
You okay with that? Okay, so this is going to cost you because the force opposing this motion gets greater. Remember the magnet down the tube? Okay, there's that magnetic friction. Okay, the magnetic force that's in opposition to that. Okay, so you got this ratio of transformers. So the number of loops is directly related to the voltage. 1 is primary, 2 is secondary. Primary means you're connected to the power supply. 2 is the appliance. And it is inversely related to the current because ideally on a transformer, the power in is equal to the power out, the rate at which energy is being transformed. That's ideally. Okay. Um, so step up, step down goes hand in hand with the number of loops and the voltage.
Okay, thank you.
Correct answer on this one is a step down. Possibly. So this primary is connected to the power supply. There are fewer loops on the secondary. Therefore, we're stepping down. There's a lower voltage because there's less loops. Correct answer is current is inversely related to the voltage. So we're stepping up. Did I say up? Yep. Stepping up the voltage, we're going to decrease the current. Current is inversely related to the voltage because the power is held constant. Okay.
So the primary coil has less loops, right?
Step up transformer. Yes.
So if it has less loops, would it have more current?
What happens to the current from the primary?
Oh, from the primary
Yeah.
to the secondary.
Yeah.
Oh.
Yeah.
Let's go.
Hey.
What? Yeah.
All right. So you're pulling a bar through a magnetic field. Which way are electrons going to be forced? Okay. So electrons, they're all moving along in the conductor. This is not a magnet, it's just a piece of metal. Electrons are being forced down here. Okay. Leaving behind protons. Okay. So everybody good with C. Out of positive into negative. So this is the direction of the electric field. Okay. Good with that? Tell your neighbor, have a conversation. Is everybody,
Much of a conversation.
yeah, is there everybody good with that? Yes. Okay. So that's your starting point. Okay. the force is going down, the electric field is going up on the electron. Electrons will be forced in the opposite direction of the electric field because they're negatively charged. Okay? So, so we're starting with this. So the electric force can be expressed as the electric field times the charge on an electron. I mean, I guess I can do this. I'm going to do Q. And magnetic force is magnetic field times the charge times the velocity perpendicular. Okay? Charges go away. So the velocity is equal to the electric field over the magnetic field. That's the lowercase v, not an uppercase v for velocity. Okay, that's this thing.
So just make it electric and that works.
Good. All right. Now, what was I going to do with that? That's the same thing. What was I doing with this?
We're probably going to find the emotional EMF.
Yes. Magnetic. Oh, here we go. I got it. I don't want to do that. This is true, but I don't want to do that. So electric field, voltage is equal to electric field times distance. Okay. Okay, so I have voltage over distance is equal to magnetic field times the velocity. And then this distance is this length of this conductor. Good with that? So that's known as motional EMF. You're moving a conductor through a magnetic field. Okay?
What's the L is the length?
Yep, L is the length. So that's your distance. Welcome. Tell your neighbor. There we go with E. You're moving parallel to the magnetic field. No force.
My piano
I mean, toughen them up. Correct answer is B. Good with that?
Like going into the page or out of the page?
Out of the page. Circle the dot. They're dots.
Oh, I was doing.
Good with that?
Yeah.
Okay. All right. So this is our simple model of a generator. Okay. So as we move this across, this is connected to a circuit. Ben Franklin people, the protons will positively charge, will go this way, the direction of current as you go this way. Electrons, negatively charged, they're going to go this way. Okay, good with that? Okay, and you can figure out the current by the induced EMF through the emotional stuff what we just derived over using Ohm's law over the resistance of the. Usually they'll stick a light bulb or something in here for like practical purposes. Okay. So to move this at a constant speed, so there's a magnetic force that's in opposition to this. This is the magnetic friction that we were talking about. Okay, so you have current going through this. So this is, you use the second right hand rule to determine the direction of current going through here. You have electrons going this way. Okay. Then you employ the second right hand rule and an additional time to figure out the direction of the magnetic force. So you have current now flowing through this wire conductor in this external magnetic field and experiences the force this way. Here's the memorized approach. This magnetic force will always be in the opposite direction of the way you're moving it.
Yeah, otherwise you have an infinite. Otherwise you have an infinite motion machine.
Right, and that's why I call it magnetic friction. Okay, so to figure out the power, a lot of times they'll use this as power. So power is equal to force times the velocity. The force is equal to the force on a wire in a magnetic field. So that's equal to the magnetic field times the current times the length of that wire that's in the magnetic field. So that's your force multiplied by your velocity, which where is all this stuff coming from? Your current is your induced EMF over the resistance. So that is what we just discovered right here. Velocity times length times magnetic field over the resistance. So we're taking that expression times this times the velocity, you get all that junk. Okay. You could also look at it just from if you had some information about the resistor. Well, no, you couldn't. These are popular free response questions because of the successive things you have to employ. Like part A, do this. Or like part A, do that. Part B, do this. Part C, do that. Okay. Yep. So I would not necessarily memorize these things, but know that that's a pretty popular series of questions. Yep. Yeah.
Sam's the problem.
Smiley yelled at me.
And also we
You
thought-
question.
I'll just, yeah, maybe you-
Yeah, I just heard about all the tests and I was like, maybe
Yeah,
I
it's
should
fine.
listen.
It's like, hey, we got to learn all this stuff quick. It's in the lab, and I was.
Here we go. Correct answer is?
C.
Correct answer is C. Into the page.
Why?
So we're moving it this way. The electrons are going to be forced down in the opposite direction of current. You can pretend that protons are going in the direction of current, being forced up. It wouldn't work this way.
Or also you can remember that magnetic force is always going to be opposite to the direction of the force moving the
You
bar.
could.
What you do right-handed?
Yeah.
No. Good question. The right-hand rule employed to this is creating a secondary magnetic field. There was an external magnetic field independent of, it is, I don't think that's going to lead you right all the time. Yeah. 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 Yes. You're holding your hand like this. So, yep, because electrons are in the opposite direction of current.
Can you do like current?
Oh.
Yes, you could. Yes. That's a secondary thing. Yes. That's legit. That won't steer you wrong. Okay. There's a lot of steps on that one.
Oh,
You take out this.
that was crazy.
It is crazy.
So not singing.
Oh, shoot. Hang on, Smiley, give me a second. I use current and electrons. Oh, I guess. Okay.
Walk your neighbor how you got to what you got.
I got 4.
Is it the change
Okay.
this way? The flux is this way.
Current
Current is going like this.
So electrons are
So
flowing.
then
I'm
the
going to
electrons are going this way. So the current field is this way.
So current electrons are flowing this way. Okay, clockwise. So then we're going to say, okay, so electron motion is this way at the top. Electron motion is this way. Magnetic field is this way, so they get pushed down. At the bottom, electrons are moving this way, like this, or magnetic field is this way.
Well, because the top and bottom cancel.
So it's those cancel each
Okay.
other out. And then
Is everybody okay with current going this way? Okay, so induced current is going counterclockwise. This guy is experiencing force down. This guy's being experiencing a force to the right. This one's experiencing a force up. These two cancel each other out. All you're left with is force to the right. Good?
Yeah, I still hate Frank like because he messed me up because I accidentally had the electrons moving with current. So against it.
Okay. And it's gonna current's going counterclockwise.
Yes.
Then you have the whole. And then you do the whole electrons are moving right now.
Okay. Oh gosh. Lower. Okay. Alright, that's pretty right. Oh.
Every time Crescendo's has a concert, it's so like games of game physics, and he's always like, I get to skip tomorrow, and I'm always
Okay. Correct.
Oh wait, it's down. Hey.
Sorry. Correct answer is B. Counterclockwise. You're okay with that? Real fast. Coming out of the page, it's weakening because you're going away from it. So the change in flux is going into the page. So the current induced in that creates a magnetic field in opposition to that counterclockwise. So I'm just gonna draw on here.
this way. Yeah, okay, I can do this. Wait, hold up. Right? When I say switch.
So did you say something to me? Sorry, I'm not paying attention.
Correct answer is
I got B.
Did I mess up left and right?
That's
left.
possible.
No.
But my right arm's the one holding the
Left
sword
is
on, so I
being.
should know that
Correct answer is B.
What? Oh, okay.
Okay. Here's your magnetic field's coming. Magnetic field's coming out of the page, and it's weaker here. Whoa. I don't care. Magnetic field's coming. No, that's sorry. Dot. My bad. Circle dot out of page. Sorry. So this is being forced to the left. This one's being forced to the right.
Oh, I did freaking non-Ben Franklin.
Okay.
Oh,
I did too.
because you have to do actual electrons.
No.
You don't have to.
But if you did this,
So you hand flat. Oh, sorry. Current. So okay. Here's just in general. It is beneficial to be a Ben Franklin follower.
Yes.
It's just more convenient. The only thing that'll bite you is a Hall effect. It's the only thing that I've found so far. Okay. So is everybody all right?
so you're using the current from the wire.
Current from the wire creates a magnetic field coming out of the page. Okay. So we got this magnetic field.
But then for the other side, is this loop?
Nope. You still use this magnetic field. So here, being forced that way.
Okay, so yeah.
And then here, still coming out, the magnetic field still coming out of the page.
Imagine trying to clock.
Over here, because it's going kind of.
Yeah. Stupid kids.
Why these up?
Current through this wire.
Oh.
I grew up with a Roman.
Okay. All right. I already told you the answer to this. It gets harder because there's more loops. There's more magnetic field in opposition to that. Okay. Correct answer is. Correct answer is B.
Don't get the mechanics of how the magnet was being held.
It wasn't being dropped.
Is dropped.
He snaps his fingers together off the top of the magnet. Like this one. Yeah.
Oh.
Also, it's not relevant to the question.
No, it really is. We use tape to hold together pencils, not to hold magnets to your skin.
Well, that's what you get strong enough for. Like, after it's
No, I have a backup.
I think you've asked him this question.
Probably.
Somebody asked.
At least 7 people have asked me this month. 7, not 70.
Okay. For the sake of time, correct answer is A. Because resistance is equal to resistivity length over cross-sectional area of the wire. There's more length. There's more wire. Okay, same, more voltage, but less current. Yeah. No. Not totally doubled. Yeah. It's because it slows down from this, and that gets.
Yeah, I can imagine that.
Yeah. Okay. Oh, I just told you that. Go slower. So here's me just expounding upon this in the last 30 seconds. This is just applications. So eddy currents. This is the whole like dropping the magnet through the pole. How it went slower. Okay. So you can use this as magnetic braking. So they do this in some electromagnetic roller coasters.
That's cool.
Okay, this is how metal detectors work. So when you've got 2 loops on either side, and when you walk through, this creates a current, induces a current in these loops that register something. That's why when you're in the airport, it goes. It has to be changing. Okay. Or if you walk through, they don't want you to walk slowly through. You have to walk. If you walk too slow, they'll make you do it again. Okay. This is also how metal detectors work. And then the last one, you could also do. You could derive this. You can derive this using Faraday's law as well. 2 different ways to do the same thing. Okay, that's it.
Walk up to the airport.
Yeah.
Smiley, I have to ask.
Yeah.
Why are you wearing your Christmas tie?
It's holiday. It's Spirit Day.
Oh! I'm sorry, Smiley. I have not paid